dive into some serious wastewater treatment theory.
Let's do it.
You sent over a bunch of resources on activated sludge models, specifically ASM1,
Yeah, those are pretty dense.
to say the least. But that's what we're here for, right?
Yeah.
To break it all down. What are these ASM things all about? And how are they used in the real world?
Well, what's interesting is that these documents you sent over, they kind of bridge the gap between the theoretical and the practical. It's one thing to have a model, but it's another thing to actually apply it to something as messy as a wastewater treatment plant.
So true.
Yeah.
So let's unpack that a bit. We've got this one here, ASM.PDF. It seems to be a learner's notes on different types of models. I have to admit, I never even really thought about types of models.
It's kind of like choosing the right tool for the job, right?
Right.
I mean, sometimes you need a simple sketch and sometimes you need a very, very detailed blueprint. It's the same when we're trying to represent complex systems like the wastewater treatment plant.
So where does ASM1 fit into all of this? We've got this other PDF here, ASMGSNG Shuki.pdf.
ASM1 is a mathematical model, but it's what we call a gray box model.
Gray box.
It means we don't know everything about what's going on.
Oh, okay.
We can't possibly account for every single one of the thousands or millions of microbial species in a treatment plant.
So you have to kind of simplify things a bit.
Yeah, we group them by their functionality, what they actually do.
Okay.
We're mainly interested in two groups. The heterotrophic bacteria, these are the ones that break down organic matter, and then the autotrophic bacteria, and these are the ones that we need for nitrification.
And both of those are measured using CODO, right?
That's right, chemical oxygen demand.
Chemical oxygen demand. Okay. So it's starting to sound a bit like a recipe here. Like you need the right ingredients in the right amounts.
It is a lot like a recipe. And just like a recipe, we use what we call yield coefficients. So that would be YH for heterotrophs and YA for autotrophs. And that tells us how much of those bacteria will grow for every unit of food or cod that they consume.
Gotcha. So this source here, ASM1-monad A.pdf, it's all about microbial growth rates, which I got to say, got a little dense for me.
Sure.
A lot of equations in that one.
The key with the Monod equation isn't necessarily the math. I think the important thing is what it represents.
Okay.
And what it's telling us is that bacterial growth isn't just about the potential for those bacteria to grow.
Right.
It's also about what the conditions in the reactor actually allow them to do.
Yeah. So it's like you could have the potential for bacteria to grow like crazy.
Yeah.
But if they don't have enough oxygen or nutrients or the right temperature, it's not going to happen.
Right, exactly. The Monod equation helps us predict how fast those bacteria are actually going to grow based on these limiting factors.
Makes sense.
Yeah, it's like saying if you're making bread and you've got tons and tons of flour and water and salt, but you only have a teaspoon of yeast, it doesn't matter how much of the other stuff you have, right?
Yeah.
That yeast is going to limit how much your bread can rise.
So in a wastewater treatment plant, oxygen could be a limiting substrate, for example.
Exactly. Or it could be nitrates or even the organic matter that they're trying to break down in the first place.
Okay.
And this source also talks about these switch functions.
Okay.
That model how some substances can completely turn a bacteria's processes on or off.
For like an on-off switch.
Yeah.
Okay.
Like oxygen, we need it for nitrification, but if we have too much of it, it can actually inhibit denitrification.
Which is another important part of the process, right?
Exactly.
So it's all about balance.
Exactly. Yeah.
Speaking of balance, some of these other sources you sent over seem to get into the real nitty-gritty of wastewater treatment. This one here, Kuva, Ipan Butuatodo, Duas.pdf, and also Dutal PuTF.
Yeah. Yeah. They get into some really important practical aspects.
Yeah, it seems like it. So we've got these practical aspects. We've got sludge age, or SRT, I guess it's called.
Right. SRT, sludge retention time. Yeah. It's basically the average amount of time that those bacteria spend in our system before we remove them.
So instead of just looking at how much sludge is in the tank, we're looking at how long it's been in there. Why is that so important?
It's all about giving the bacteria enough time to do their job.
Right.
These documents, especially the shuchudong.pdf, they actually give us formulas for calculating the minimum SRT, the minimum sludge age that we need for these processes to work.
Wow.
Mhm.
So instead of just like, I don't know, using a rule of thumb, we're just guessing.
Yeah, it's much more precise.
We can actually calculate this based on things like temperature, the volume of the different zones in our reactor.
Exactly.
Interesting.
It takes into account a lot of different factors. It's a lot more nuanced than just saying, okay, well, this is your SV30 and this is your sludge concentration.
Yeah.
We can really fine tune it by understanding sludge age.
Wow. This is really making me rethink how I view, wastewater treatment. It's like it's not just about pipes and tanks, it's about managing this whole biological system.
That's exactly right. And we haven't even gotten to, what I would call the unsung hero of wastewater treatment, which is the secondary clarifier,
Okay.
the settling tank.
Right.
Yeah,
Okay, JDADF.
that's the one.
Yeah. Yeah, this source really emphasizes how important it is to get that settling process just right.
Yeah. Because I have to admit, I kind of thought of the clarifier as just this big tank where you just let things settle out. Like, what's so complicated about that?
Well, you're right. It seems pretty straightforward, but it turns out that getting that settling right is actually crucial. And this is another area where modeling comes in.
Okay.
This source suggests using what they call one-dimensional models.
One dimensional.
Yeah.
So, not like those fancy 3D computational fluid dynamics models you sometimes see. Exactly. We're not trying to model every little swirl and eddy.
Okay.
What we want is just a simplified representation of how that sludge moves as it settles and how that clarified water moves upward.
So it's about finding that balance again, right?
Yeah.
Between accuracy and complexity.
Yeah, exactly. And this source really highlights how those simpler models can be really helpful for optimizing things like the sludge settling characteristics, how much of that sludge we recycle back to the bioreactor, and ultimately how clean that final effluent is.
It really strikes me how we can take these biological systems, simplify them into these models, and then use those models to actually like fine tune and really optimize a process.
Yeah, it's a really cool example of how we can apply science to solve real world problems. And speaking of real world applications, this document here, ASM1's.pdf, it talks about some of the challenges and rewards of actually using ASM1 in practice.
Yeah, it gives that example of a team of really experienced engineers, and they were relying on intuition and like quick back of the envelope calculations to troubleshoot this plan. It's interesting how, even with these fancy models, experience still matters.
Oh, absolutely.
Yeah.
There's no replacement for that kind of expertise that comes from years of working with these systems. But this source also highlights that, even those very experienced engineers, they can still benefit from a deeper understanding of the models.
It's like having another tool in their toolbox.
Exactly, like having a secret weapon, right?
Yeah.
To help them solve those really tricky problems. And I love that this document also mentions that the author actually developed an online ASM1 calculation tool.
Oh, really?
Yeah, it's like they're really trying to make this knowledge more accessible.
That's great.
Take it out of the textbooks and put it into the hands of practitioners.
Yeah, I love that. Okay, so we've talked about, heterotrophic, autotrophic bacteria, yield coefficients, Medot equations, sludge age. But how does it all come together in the ASM1 model itself? Like, what does that actually look like?
Well, that's where this ASM1.pdf document really shines. It gets into the nitty gritty of how ASM1 actually works.
Okay.
And at its core, ASM1 uses what we call a matrix to represent all the different substrates and processes going on in that system.
A matrix, like something out of a math textbook.
Yeah, it sounds a little intimidating, but it's actually not as bad as it seems.
Okay.
Think of it like a big spreadsheet.
Okay.
And each row of that spreadsheet represents a different substrate. So that's things like your organic matter, ammonia, nitrates.
Right. Okay.
And then each column, it represents a different process. So that could be like growth of heterotrophs, growth of autotrophs, things like that.
Okay.
And then each cell in that matrix, it contains the equation that describes how that specific substrate is affected by that particular process.
So it's kind of like this giant, like, recipe book.
It is like a recipe book.
Yeah. Where each recipe is a different interaction happening in the wastewater treatment plant.
Exactly.
Okay.
And by using this matrix, ASM1 lets us track the fate of each of those substrates as it moves through the system.
Okay, so what about those switch functions that we were talking about earlier? Like, how do they fit into this whole matrix?
So those are actually built right into those equations.
Okay.
So for example, the equation for how heterotrophic bacteria grow in the absence of oxygen, it would include a switch function that basically turns off their oxygen consuming activity.
Oh, okay. So it's like depending on the conditions in the tank, the model's going to use slightly different equations to represent how the bacteria are behaving.
Exactly.
Interesting.
And that's what makes it so powerful is that it can dynamically adjust based on the conditions in the plant.
This is getting complicated. So, do you need like a supercomputer to run these models? Like, are we talking teams of mathematicians to make this work?
Not necessarily. I mean, ASM1 can get complex, but we have software now that can do those calculations for us.
Okay.
So we can input the data about our wastewater, about our plant's operating conditions, and the software can crunch those numbers and tell us what's going on.
So you can have like almost like a virtual wastewater treatment plant on your computer
Yeah,
and run all these simulations.
exactly. Yeah, we can run simulations, we can test out different scenarios, all without having to make changes to the real plant.
That's awesome. It's like a really powerful tool. This source, Orshige,
Mm.
DWAT-Kin, Dasaigot PDF, really emphasizes, making sure we're using real world data.
Mm.
Like we can have our fancy model, but if it doesn't match what's actually happening,
Right. You have to ground it in reality.
exactly.
That's where calibration and validation come in.
Okay.
You have to adjust your model to match the real world.
It's like tuning an instrument, right?
Yeah.
Like you need to make sure it's playing the right notes before you can start making music.
Exactly. A well calibrated model can be a really powerful tool for optimizing those processes.
This has been really eye-opening. I mean, we went from what I thought was going to be just like, oh yeah, the secondary clarifier, it's a big tank,
Right.
but it's so much more. And the fact that we can model that and understand those processes, it really makes you appreciate how complex wastewater treatment really is.
It really is. Every time you flush the toilet, there's this whole hidden world at work.
Exactly.
Yeah.
This source, John on TDF, it mentions that ASM1, while powerful, it's still just one piece of the puzzle.
Right.
Like we need to understand the clarifier. We need to have those real world data points.
It's all connected.
Yeah, it is. It's amazing to me how something like a clarifier, which I always thought of as just this big tank, could be so complex.
It is. You look at a wastewater treatment plant and you think, pipes, tanks, what's the big deal?
Right.
But when you really dig into it, like this source does, it's like, wow, there's a lot going on in that clarifier.
Yeah. And this source actually has this great diagram. I love when these sources have visuals.
Me too. It helps.
It really shows all the different factors that can affect how well it performs.
Yeah.
Like the incoming flow rate, how much sludge we're sending back from the bioreactor, even like where we introduce that flow into the tank.
All those little details matter.
It does. Everything's connected.
It is, yeah. And this source also talks about how important the operator is in all of this.
Okay.
We can have our fancy models, we can have our automated systems, but at the end of the day, you need a skilled operator to make it all work.
That human element.
Exactly. And it's like the operator is like the conductor of an orchestra, right?
Mm,
They're using their knowledge, their experience to fine tune each process.
I like that. The conductor of the wastewater treatment orchestra.
That's right. Making sure it all works together.
Yeah. This source even suggests using these models for things like operator training,
Oh, that's interesting.
which I thought was really fascinating. Imagine you can give operators this safe space to run simulations, try different things, see how their actions impact the process.
It's like a flight simulator for wastewater treatment plant operators.
Exactly.
That's a great analogy.
That's cool. It seems like a lot of this comes down to, how do we make this knowledge more accessible? I love how this source talks about like how do we make these tools as easy to use as like a smartphone app?
Right, exactly. I mean, that's the ultimate goal, right? To put this powerful knowledge into the hands of as many people as possible.
Yeah, democratize it a little bit.
Exactly. And it's only by doing that that we can really, I think, unlock the full potential of these models and really revolutionize the way we treat wastewater.
So to kind of wrap things up here, I mean, this has been an incredible journey.
It has.
We went from feeling honestly a little overwhelmed by these activated sludge models to like exploring this whole new world.
Yeah, I think that's the beauty of these deep dives that we do.
It is.
We start with these complex topics and we unpack them and we find these really interesting insights.
Yeah, we've looked at the science behind it, the practical applications. We even talked about the role of the operator.
And I think the most important thing is that it makes you realize that wastewater treatment, it's not just this like out of sight, out of mind thing.
Right.
It's crucial. It's protecting our environment. And it's something that we need to be thinking about and talking about more.
Absolutely. Well, on that note, thanks for coming on this deep dive with me. It was a lot of fun. And for everyone listening, we'll see you next time on
The deep dive.
the deep dive.